A very good evening to one and all. Alamos National Laboratory. This work of evaluating lock-free parallel programs has been conducted while I was a PhD student at the University of Limerick with Professor Kana Ryan and Dr. Arathi Fajad. For the next few minutes, I will be explaining you why we should care about the evaluation of lock-free parallel programs and how we accomplish this objective and what are the experimental results that we observed. And before we finally conclude, we discuss and analyze the evolved parallel programs in this approach. Let us imagine we have a 4-core processor. When we execute a sequential program on this 4-core processor, it exploits the computational capability of one of those 4 cores by wasting the remaining 3 cores computational capacity. Ideally, we want this program to be executed across all the 4 cores. Thereby, we fully realize the computational power of these cores. And to do that task, we have to write parallel programs. But writing parallel programs is an expert's thing to do, because we're all trained to think sequentially and write sequential programs. Imagine we have written a parallel program, being an expert. That doesn't solve our problem completely. This is an example of a Fibonacci parallel program where it has a critical section in its parallel region. This is the entire parallel region. It has a couple of critical sections. What happens in that critical section is a bunch of threads executing in a parallel region will enter into the critical section, where in the critical section only one thread is going to be executed, while the remaining threads are going to wait and sitting idly. In this critical section, the shared resources are locked for that thread under execution, and therefore here we are losing in terms of the execution time. Our solution for this is to produce to evolve lock-free parallel programs automatically using grammatical evolution. This is an enhancement to our previous work, which we published in Gecko last year and EuroGP. Writing lock-free parallel programs is actually again an expert's thing, and often experts and the programming gurus fail to write correct lock-free programs. That means we can imagine how difficult it is to manually write or code lock-free parallel programs. Hence, that justifies the task of automation is necessary in this era. And we apply, as I said, we apply grammatical evolution for accomplishing this task, and the whole community is familiar with the algorithm. I'm not going to spend much of my time explaining this thing, as we are short of the time. I'm going straight into my methodology, which is the automatic lock-free parallel programming. We have 2 primary components in this, which is the way that we design the grammars and the way that we evaluate the fitness of the evolving lock-free. And this is an example grammar for evolving Fibonacci lock-free parallel programs. In this, we have included the OpenMP parallelization pragmas, which have both task and data parallelism pragmas. We create a space of OpenMP parallel programs where we include the problem-specific information of what are the shared variables, what are the private variables, and also we include within this space we include the atomic GNU GCC atomic primitives that guarantee the lock freedomness in the evolving programs. That's the grammar design. When we go on to the way that we evaluate the fitness evaluation of the evolving parallel programs, we consider the execution time of the evolving lock-free program, and we measure the mean absolute error of the evolving programs, which guarantee us the correctness of the programs. And we experiment our approach on 5 benchmark recursive problems, which are standard in the program synthesis domain, which are the sum of n numbers, factorial of a number, and a Fibonacci program, binary sum, which is adding the 2 adjacent elements of an array, reversing the list or an array of elements. In that, input is the type of the arguments and while the output is the return type of the end result for each program, and they are the local variables, again problem specific information, and they range from where we draw the random numbers for each problem. And we keep the standard GE parameters consistent for our experiments, and we use an Intel Xeon 16-core multi-core processor, 16-core processor, which act as 32 cores upon enabling the hyperthreading. And we use OpenMP get W time to measure the execution time of the parallel program. We record two measures. One is the average execution time in these results, in these experiments, and the speed up. Average execution time is the sum of the best evolving programs in each run across all the runs, which is averaged across all the runs. And the speed up is the AET of one core over AET of n cores. Average execution time, when we compare these results on 2 cores, 4 cores, 8 cores, and 16 cores against the standard GE producing sequential programs, it is evident that the execution time AET results are significantly better on 4 cores, 8 cores, and 16 cores in comparison with the standard programs. They are not so significant for 2 cores because of owing to some scheduling issues, thread scheduling issues, and operating system scalability issues, which are entirely a different story. But for now, we can clearly see that there is some kind of parallelism in these programs. And then now with that confidence, we are going to compare the speed up results of ALP with our previous approach, which is MCGE2, that evolves pure parallel programs rather than lock-free parallel programs. And the result is that ALP is beating the pure parallel programs produced by our previous approach. When we see the efficiency of our approach, the ALP evolved parallel programs are significantly better on 4, 8, 16 cores, as I said before. When we look at the efficiency, they are only efficient on 8 and 16 cores. On 2 and 4 cores, they are pretty much similar to what MCGE2 are. MCGE2 results are showing it to us. When we look at the best program, one of the evolved best programs, we see that we have sync, fetch, and add. Let us say, and then another again sync, fetch, and add, which is second recursive call for the Fibonacci program. Let us say one of that calls, let us say this call is going to be replaced with sync, fetch, and sub, which is an infeasible solution. Instead of adding the results to adding the call to the result, it is subtracting the result. Thereby it became an infeasible solution. That means this is one of the limitations, which is purely to do with the way that the search process in GE works, and that is a limitation which we'll discuss further in this presentation. And then now we wanted to compare how good we are performing against the human written parallel programs. Now the ALP produced lock-free programs efficiency on 8 and 16 cores are compared against the human written parallel programs, and we see that these programs are competing, but they are not really beating the human written parallel programs. That means we are pretty much good at the evolution, that at least we are competing with the human written parallel programs. And coming back to the limitations that we have in this system, ALP, yes, again, generation of the infeasible solutions, which I said we have to tweak the way that GE search process works. Maybe consider the usage of enhancing the GE search process by exploring the recent advancements in GP community, which is semantic GP, applying that in the GE search algorithm. That might help us in reducing the infeasible solutions, if not completely avoid what it is being produced. And then atomicity might fail sometimes because the GNU GCC atomic operations are only capable of writing 16 bytes of sizes into the memory, while they might fail if it is a 32 byte write into the memory. So these are the potential limitations. And finally, the take-home message is that we can able to produce parallel programs, which are not just parallel programs, but they are lock-free parallel programs. They compete with the human-written parallel programs. And for the future work, we want to play around with the memory ordering operations. And again, in the next direction, we want to scale up the application or the problem domain. And then for that, Xbox console is a best fit. It has a much better potential for writing lock-free parallel programs. And finally, I would like to thank SFI for funding this project, and BDS Group for supporting me with their expert advice, and the GI and community, SBSE community, and the organizers for generously understanding my situation of not being able to travel and my visa issues. So thanks a lot.